Vast oceans of truth lie undiscovered before me. For a voyage into the mysteries of the universe, welcome to the Cosmic Front. Today's adventure begins at NASA's Goddard Space Flight Center in Maryland. This is NASA's premier control center for satellites navigating outer space. From this very room, commands go out to the Hubble Space Telescope. Hubble has been illuminating one mystery of the universe after another. With no atmospheric distortions, a space-based telescope can observe celestial bodies in great detail. Omega Centauri is a star cluster containing 100,000 stars. One can make out the blue or red colors of individual stars. This is the Cat's Eye Nebula. Those veils enshrouding it are gases released by the star that shines in its center. Many gaseous layers, distinctly revealed. This huge galaxy contains 100 billion stars burning in space like our own sun. Even at the speed of light, its image takes 69 million years to reach us. This is one far-out celestial body. Hubble beautifully captures an image of this entire galaxy, showing even individual stars. The Hubble telescope's gorgeous, unforgettable images lure us ever further into the cosmos. Hubble has taken over 600,000 images so far. Every image is imbued with the adventurous spirit of scientists across the globe. Scientists at the Cosmic Front. Hubble is now shedding light on one of the greatest mysteries of the age: the distribution of galaxies in space. There are over 100 billion galaxies in our universe, spread out in a fantastic pattern. And that pattern is bubbles. Entire galaxies clinging to each other in a pattern resembling, astonishingly, that of soap bubbles. But in the bubbles themselves, there are no galaxies. How is it that the universe is structured like this? The Hubble Space Telescope takes on the challenge of the universe's bubbles.
1, and liftoff of the Space Shuttle Discovery with the Hubble Space Telescope, our window on the universe.
The Hubble Space Telescope was launched into Earth orbit aboard the Space Shuttle in April of 1990. It's the largest ever space-based telescope, 13 meters long, as big as a bus. It photographs the cosmos while traveling at 28,000 kilometers an hour, at an altitude of 600 kilometers above Earth. The Space Shuttle has been used to service the telescope. In 2009, state-of-the-art observation equipment was installed, upgrading its capabilities. Let's check out just how powerful the Hubble is. The Orion Nebula. Gases in vivid reds and blues. Let's go in for a closer look. Amidst these cosmic clouds, a strange celestial body appears. This heavenly eyeball is a protostar. It's the beginnings of what will eventually be a star shining brightly like our own sun. Only the Hubble Space Telescope, with its amazing powers of resolution, could penetrate to the very nucleus of this incipient star system. This one is like a budding flower. Hubble photographed it at intervals for half a year. Its unfolding petals of gas or cosmic dust are rendered in exquisite detail. This remarkable spherical structure, floating in space, is the remnant of a supernova that exploded some 400 years ago. Hubble was able to capture the faint color of its nearly transparent shell of gases. Even without atmospheric interference, it's quite a trick to capture the light of such far-off sources. The light is collected and focused by a giant 2.4-meter diameter mirror developed especially for use in space. Light rays are directed to cameras situated behind the mirror, and various data are then beamed back to Earth. Moving through space at incredible speed, it takes Hubble just 90 minutes to orbit the Earth. All the while, it can maintain focus on a fixed point in space, collecting optical and spectrographic data. This is the Hubble Command Center. Let's check out the very heart of mission operations here, the control room. A staff of 10 or so working in shifts command the Hubble 24 hours a day.
This is the mission operations room of the Hubble Space Telescope at Goddard Space Flight Center. We have a number of consoles in here. Each has a specialized function and position. This map is currently, this is where the Hubble is over ground. We're over North Africa right now. This is the pointing control system and optical telescope assembly, as well as the science instruments. Rosalie is monitoring the performance of the onboard attitude control systems.
The staff send out a stream of vital commands, specifying minutely how the angle of the telescope should be adjusted and how long a given observation will last. This is the first place on Earth to receive the images shot by the Hubble Space Telescope. And this is where the staff decide where to focus Hubble's observations to begin with. In fact, they're deliberating right now. Provided a proposal is formally submitted and approved, Hubble can be used by anyone in the world. Every year, the Institute receives 1,000 such proposals. Of those, it will adopt about 200, with 800 falling by the wayside. The Institute's director is Matt Mountain. He says that, as director, he greatly enjoys evaluating the many splendid proposals for use of the Hubble. His toughest task is dealing with complaints from those whose applications were denied.
Sometimes I get a lot of very angry calls for some very experienced astronomers complaining, why haven't I won telescope time? After all, I'm a famous astronomer. And I have to tell them, I'm afraid this year your idea was not as good as the idea of, in fact, some younger people. Hubble is a world telescope. It's everybody's telescope. It's the people's telescope. And I think that we should all be very proud that as a people, we're able to do this.
If a proposal is approved, actual observations are initiated. Some observations take several hours. Some take dozens of hours. But the raw images that reach Earth are not, at first sight, breathtakingly beautiful. They must undergo several steps of processing first. The first step is to delete extraneous optical artifacts.
Yeah, so this first image here is what you might call a raw image. It comes down from the telescope, and we spend a lot of time here calibrating our cameras so that we understand the artifacts that you will see in the images. And of course, we want to remove those artifacts from the image to get a nice clean image.
These raw images that first arrive on Earth are marred by cosmic rays and other factors. By superimposing multiple images and removing visual noise, a clean image can be obtained. Next, represent the object in color, based on the observational data. The Hubble Space Telescope does this by recording image data using more than one color filter, and then combining the results.
They took the data with the Hubble Space Telescope for doing science, but as kind of as a byproduct, these images are often very attractive, beautiful images, and we would like to make these available to the public as much as possible.
Hubble's data can also yield three-dimensional images.
Right now, a lot of the bright stars we keep in the foreground, many of the faint stars we keep in the background. It's obvious that way. So first I have to take out all the stars. So all the stars are removed from the image. And then we place placeholders where the stars are, a sample template of where the stars are. Then I classify them on which ones are close and which ones are going to be far away.
In the contours of a Hubble image, gases and stars are clearly differentiated. Distributing them according to their measured distances results in 3D images. Exciting images, born of the desire of scientists to convey the wonders of the cosmos. the freshness and immediacy of Hubble's images enhance our understanding of the universe. The Carina Nebula comprises vast gaseous clouds. It measures 50 light-years across. Just like people, stars in outer space are born and later die. They originate, it is believed, from clouds of gas and dust. The dark portions of this image are dense concentrations of accumulated gases. It is within these dense gases that stars are born. This is a location within the Carina Nebula. We see towering masses of gas. With this image, Hubble has captured the very moment of a star's birth. Stars are born amidst violent eruptions. Here, we see a jet erupting at the tip of a tower of gas. Stars do not live forever, and within this same Hubble image of the Carina Nebula, we can find a spectacular view of a star that is dying. Amidst gases expanding like two balloons fused together, a giant star is entering its final phase. Superannuated, it marks the end with fierce exhalations of gas and dust. A grand explosion is the last hurrah of the giant star. The Crab Nebula is comprised of the remnants of a star that exploded a millennium ago. The power of that explosion was tremendous. Even now, its gases are expanding at a rate of 1,300 kilometers per second. Eventually, these gases will coalesce again as the raw materials for new stars. The Hubble Space Telescope has succeeded in capturing detailed images of the life and death of these stars. Hubble's precise images also help us understand how the cosmos is composed. The universe, we find, is structured into clusters of galaxies, collections of stars. This is our own galaxy, the Milky Way. It's 100,000 light-years across. That means that traversing it would take 100,000 years at the speed of light. Planet Earth is located here, between two thick swirling arms of the galaxy. And beyond the Milky Way, vast numbers of other galaxies can be found, out to the farthest reaches of the universe. One by one, Hubble has been capturing detailed images of many of the uniquely shaped galaxies in our universe. This is the Whirlpool Galaxy, located 21 million light-years from Earth. One can clearly make out the red nebulae on its giant spiraling arms. It's about the same size as our own Milky Way galaxy. Galaxy Messier 104 has been nicknamed the Sombrero Galaxy. You can see why from this profile. The bulging center and the broad, thin disk are two striking features of this spiral galaxy. Galaxy Messier 82 shoots forth clouds of interstellar matter. These red plumes bursting out from the center are made of hydrogen gas. Here is a pair of galaxies 100 million light-years from Earth. The two galaxies are beginning to collide. Ultimately, they will merge, forming one giant galaxy. Such collisions tend to occur in areas where galaxies are found in high concentration. But why are there such clusterings of galaxies? To solve that mystery, a large project initiated by one scientist has set a record for observation time using the Hubble Space Telescope. The suburbs of Los Angeles. Astronomer Nick Scoville has been observing far-off galaxies for 4 decades. His chief goal, to solve the mystery of galactic clustering.
So, Doctor, what are you working on?
This is a table which I made recently, a couple months ago, which I'm now tightening up. It's a suspended table, no legs, no compression members, just wires to hold it up. If you think about it, the table is a little bit like a spiral galaxy in the sense that it's suspended in space. But it's an amazing thing when you look at galaxies that they're actually suspended in space, nothing holding them up except gravity of very distant galaxies.
Astronomy requires a lot of creativity. So in his spare time, Scoville likes to make things.
We still don't understand the real origin of it. And so, even though astronomers have gained an incredible knowledge and understanding of the present universe, there's a lot that's left out. And that's one of the real pleasures of doing astrophysical science.
A major discovery relating to galactic distribution provided Scoville with the hint he needed to solve one of his puzzles. In 1986, articles in American newspapers trumpeted the view that the cosmos was structured like a conglomeration of bubbles. This news, which ran completely counter to conventional wisdom, was a great shock to cosmologists.
To do that,
the co-discoverer of this bubble structure was the astronomer Margaret Geller. She remembers how scientists at the time generally discounted galactic clusters, seeing primarily a loose scattering of galaxies.
they were just randomly distributed in the universe, and then there were some clusters of galaxies, people knew about those, and they thought they were just, there were some lumps around in the universe, and they were random. And we analyzed then roughly 1,000 galaxies had known positions in three-dimensional space. And so, in fact, we were really looking to show that there weren't any.
With planet Earth as a reference point, Geller mapped the locations of 1,000 galaxies. That led to the discovery of strange patterns in galactic distribution.
And you can see that there's a pattern. It looks sort of like a person. And you can see there are regions that are really empty where there are no galaxies, like this one. Very big and very beautiful patterns. And it was a very exciting, heady experience to find those. And I like to think of it as a kind of bubble-like pattern. But these bubbles aren't the tiny bubbles you see in your kitchen sink. These bubbles are 200 million light years across. So it takes, traveling at the speed of light, it would take 200 million years to cross one.
There are vast regions in space where there are almost no galaxies, and other regions where they are stacked up like a wall. It's as if the galaxies were clustered in the interstices between giant bubbles. The galaxies are indeed distributed according to a general principle. Geller calls it the universe's bubble structure. However, some objected that Geller's scope was too narrow and that the bubble-like distribution she observed was merely accidental. The state of New Mexico, in the western United States. At the Apache Point Observatory, perched atop a mountain range, scientists from America, Japan, and Germany have mapped out the bubble structure of a large section of the cosmos. The project is called the Sloan Digital Sky Survey, or SDSS. A dedicated 2.5-meter aperture telescope was specially fabricated for this project. The initial target area for observation was 100 times larger than Geller's, about half of the nighttime sky. Galaxies within that scope were cataloged and their distances from Earth measured. The tiny holes in this metal plate help measure galaxies' distance from Earth. First, the two-dimensional location of each galaxy is marked with a hole. From the spectroscopic data gathered through dedicated optical fibers attached to each hole, the corresponding galaxy's distance from Earth can be calculated. The survey utilized 2,000 of these metal plates. In the first 8 years, half of the sky was surveyed. This is a partial map of the universe, based on galactic distances as determined by the SDSS project. Each of these spots is a galaxy. There are 1 million of them. In some places, galaxies are densely congregated. In others, they are sparse. Such bubble structures extend indefinitely, in all directions. The universe is just full of bubbles. Nick Scoville of Caltech is the prime mover behind the Cosmos project, designed to observe extremely distant bubble structures. Using the Hubble telescope, it should be possible to peer beyond the SDSS project's 3 billion light-year range to as far as 10 billion light-years from Earth. By looking that far away, Scoville hopes to observe the past shape of the bubble structure. This galaxy is located 320 million light-years from Earth. In other words, its light takes 320 million years to reach us. So the light we're observing is from 320 million years in the past. The farther out one looks, the farther into the past one sees. Scoville believes that the bubble structure's past can help us unravel such mysteries as why the galaxies cluster the way they do, and why vast reaches of space have emerged with almost no galaxies.
The prime goal of the Cosmos project, which separates it from other deep surveys done with Hubble, is that it covers a large area, and the prime goal is, as it was originally designed, is to map the structure of galaxies and understand their evolution with respect to the large-scale cosmic environment.
The new proposal, however, had a serious constraint. A huge amount of time was required for these observations. Consider the full moon. Mapping its area requires 80 separate images. But observing the bubble structure of the universe required mapping at least one enormous bubble, plus some margin. That would take as much sky area as 9 full moons. The hundreds of images necessary meant securing huge amounts of telescope time with the Hubble. To succeed in such a large-scale survey, project leader Nick Scoville assembled a team of more than 100 scientists from around the world. It is a remarkable international undertaking, one that has been conducted successfully for many years. In 2002, the Cosmos project submitted its initial proposal for use of the Hubble Space Telescope. But it requested so much telescope time that the Hubble's project review panels could not come to a decision. The Hubble director at that time was Stephen Beckwith.
I think it was something like 1,200 orbits of telescope time, which no project had ever had before. We only give out 3,000 orbits in an entire year, so this would have been more than a third of an entire year's worth of data. And even though the committees thought the science was good, I think they couldn't quite bring themselves to give out that much time.
The policy had been to give as many scientists as possible access to Hubble. But Beckwith wrestled with the issue. He was reluctant to veto the project. Some large-scale programs were just too worthy to pass up.
Even if you normalized per orbit of telescope time, the impact of those programs per orbit was greater than the sum of all the small programs per orbit. And then as director, I took a fraction of the telescope time and I set it aside, and I said that will only go for very large programs.
Under this new regime, the Cosmos project qualified as a large-scale Hubble program. One of the project's team members was Yoshiaki Taniguchi of Ehime University in Japan.
よくぞハブル宇宙望遠鏡はこのプログラムを採択してくれたなと まあそうなってほしいっていう気持ちは当然あるんですけども、でも厳しいよなっていうのはそれはみんな思っていることなんで驚きましたね。
They didn't get as much telescope time as they'd requested, but it was a record amount anyway. 666 Hubble orbits, or 1,000 hours. Scoville also figured out how, in the reduced time available, they could adjust their imaging methods to cover an area as large as 9 full moons. In 2003, Hubble began observations dedicated to resolving the mystery of the universe's bubble structure. The target field, measuring 9 full moons across the sky, but extending deep into space, focused on a corner of the Sextans constellation. Let's take a look at some of the 600 images taken during this project's record-breaking number of Hubble orbits. What at first glance look like stars are in fact mostly galaxies. Let's look closer. Galactic forms come into view. Smaller-looking objects may simply be farther away. Some of these galaxies are more than 10 billion light-years away. In that 9 full-moon field of observation, over 1 million galaxies were detected. It took 3 years just to analyze these images. This image represents the distribution of galaxies as recorded by the Cosmos project. The red portions indicate the presence of galaxies. The brighter the area, the denser the galactic cluster.
So within this particular structure here, there are about 1,000 galaxies. There are filaments leading into the structure, 1,000 galaxies occurring within it. Large structure down in here, filaments coming across the field.
That 9 full-moon field of observation did in fact yield proof of the universe's bubble structure. And the Cosmos project captured images of galaxies from a whole range of time periods. The galaxies are differentiated by distance from Earth, so one can trace the shapes of bubble structures into the past. The basic principle: the farther out in space one looks, the farther back in time one sees. This is outer space. 2.5 billion years ago. One can readily make out large bubble structures. Let's go even farther back in time. $3.5 billion years ago. The bubble structures are a little smaller. $6 billion years ago. The bubble structures are much smaller. Farther away and longer ago, they were smaller still. Using the Hubble Space Telescope, they found that the farther back in time they went, the smaller the bubble structures were. A million galaxies, from 10 billion years ago to the present day, all photographed thanks to unprecedented access to the Hubble Space Telescope. This reveals, in part, the evolution of the universe's bubble structure. And somewhere in these million galaxies is hidden the key to the origin of that bubble structure. The Cosmos project has analyzed every one of those million galaxies.
You want to show some, Peter?
Sure. So we now have over 25,000.
Let's see what light it has shed on the mystery of cosmic bubble structures.
6, which is 500 million years after the Big Bang.
So it's actually really interesting because there are some
Alexei Leotode conducts image analysis for the Cosmos project. Multilingual, she was interviewed for this program in Japanese.
This is using taller Fisher. 私たちは地球に住んでますね。宇宙を見るとすごいたくさんの銀河が見えます。ものすごくたくさん見えます。例えばコスモスの中では銀河は100万ぐらいの銀河が見えます。もし地球と銀河の間、空っぽだったら、この銀河からの光はまっすぐ望遠鏡に来ます。でも、もしこの銀河の間、暗黒物質があるとします。この暗黒物質はとても重いです。重さはだいたい私たちの太陽の重さかける15乗ぐらい。だからとっても重いです。アインシュタインの General Theory of Relativity を勉強すると、これはとっても重いので、銀河からの光はまっすぐ来るんじゃなくて曲がってきます。これは強い重力レンズと言います。
So the dark matter distorts light in what's called gravitational lensing. This dark matter cannot be seen, but altogether its mass is more than 5 times the mass of all the stars and galaxies. That makes it a source of powerful gravitational forces. Because there is dark matter between the Hubble and far-off galaxies, the light from those galaxies is bent by gravitational lensing. In this image from the Hubble Space Telescope, we can see typical gravitational lensing. The pole of the invisible dark matter makes far-off galaxies appear curved like bows. By analyzing how light is transformed by gravitational lensing, we can get a sense of the distribution of dark matter.
Rachel,
That has meant studying an enormous number of galaxies and considering a whole range of gravitational lensing effects. The analysis took 2 years. Finally, the distribution of dark matter over a wide area was made manifest. This is the distribution of dark matter, as revealed by the analysis of gravitational lensing. As with the galaxies, there are areas of clustering and there are empty areas. In fact, the dark matter also demonstrates a bubble structure. On the left, we see how certain galaxies are distributed. Let's map onto it the dark matter for the same area. It's an exact fit. Dark matter is distributed in the same places as the galaxies. Where there is no dark matter, there are no galaxies. The bubble structure itself is determined by dark matter. Dark matter. Within its powerful gravitational fields, stars and galaxies have congregated.
実際それが宇宙空間に まあ雲のようにこう分布してて、しかもその暗黒物質の塊の中でちゃんとこう銀河が生まれて育ってきてると。つまり本当に暗黒物質にこう導かれて銀河が生まれて進化してきたんだなっていうことが実感として分かったっていうことがあってですね、やっぱりもうそれまでこうモヤモヤしたものがそこで一気に解決したっていう気持ちがありましたね。でもまあこれはちょっとやっぱり疑い。
Using Japan's Subaru telescope, Taniguchi checked the distances of those 1 million galaxies identified by Hubble. Confirming the distances of 1 million galaxies took 3 years. That data enabled the construction of a three-dimensional view of the dark matter. This is the first 3D map of dark matter ever seen by human eyes. Inside the regions of dark matter, cosmic gases and dust collect, giving rise to stars and galaxies. Research into the distribution of dark matter is now one of the hottest topics on the cosmic front. Seeking to elucidate the bubble structure of galactic distribution, scientists in the Cosmos project took on some of the toughest problems in astrophysics. The Hubble Space Telescope's catalog of so many galaxies constitutes a treasure trove of information, and Nick Scoville expects that with further conceptual advances, it will continue to yield discoveries.
I think the most critical thing that a good astrophysicist should have is the curiosity to, one, discover problems which people have either misunderstood or haven't solved, but then secondly, to persist in trying to understand what they're seeing. Like this table concept, which I wanted to build for a very long time, but didn't have the time or didn't have the design. And, you know, it's a lot of fun to keep a problem in the back of your mind, let it percolate, and then eventually come back and work on it. And you accumulate new knowledge over time, which then you apply to that problem. Looks like it's still holding.
Applying the same curiosity and persistence, Scoville plans to continue his pursuit of knowledge on the cosmic front. What was the universe like when its bubble structure first formed? Let's meet a scientist dedicated to this new issue on the cosmic front. Mauna Kea, Hawaii. Ranging over the summit of this 4,200-meter volcano are the astronomical observatories of 11 nations. This is Japan's Subaru telescope. Its 8.5-meter primary mirror is among the largest in the world. It can take in 10 times as much light as the Hubble Space Telescope. That means it can capture even fainter objects than Hubble can. A celestial object spotted by the Subaru telescope in 2007 was like nothing that had ever been seen before. The discoverer was a young astronomer named Masami Ouchi. Ouchi was observing distant galaxies with the aid of the Subaru telescope. In the course of that, he accidentally came across a curious object. What he saw was in this image. Of course, many galaxies are shown. It's this red object that was so problematic. Distance from Earth? 12.9 billion light-years. That dates it to near the very birth of the universe. Detailed analysis established an astonishing fact. The object itself spanned 50,000 light-years. This was on a scale unthinkable in conventional cosmology. Galaxies are the largest objects in the universe. But when the Hubble images are lined up, one sees that the farther back in time one goes, the smaller the galaxy. Previous measurements put ancient galaxies at about 10,000 light-years across. If the object spotted by Ouchi was a galaxy, its size was unprecedented for that slice of outer space.
こんなに大きいんだから、これは近くの銀河で何らかのその誤差とかエラーで遠くの銀河だと思ってそのサンプルに入れてしまったものだというふうに最初は思っていました。
It was so unbelievably large, Ouchi initially removed it from the study, thinking it a measurement error.
I mean, the pointing is fine or...
But somehow it bothered him, so he took additional distance measurements at the Keck Observatory. The result was the same, 12.9 billion light-years. The distance measured with the Subaru telescope had not been a mistake.
これはすごいというふうに思って、うわーというちょっと叫び声みたいなものをちょっと上げてしまいました。
Ouchi named the object Himiko after an ancient Japanese queen. 5 times larger than any other galaxy that old, Himiko was a mystery. Exactly what was it? If Himiko's shape could be more accurately determined, that would point to an answer. And the best tool to help with that was the Hubble Space Telescope. In February of 2010, Ouchi submitted a research proposal for use of the Hubble telescope. The following June, he received a reply from the Hubble director, Matt Mountain. It announced straight off that his proposal had been approved. He had been granted telescope time during Hubble's cycle 18 to photograph Himiko. In September, Hubble set its sights on Himiko. What would Hubble reveal about Himiko's shape? All the data was relayed to Earth.
そうですね、少し緊張してます。やっぱり新しいデータを見るというその前はやっぱり緊張するものですね。
This is it. Download time. This will be Ouchi's very first Hubble's eye view of Himiko.
Oh, これだ。細いな。どんな印象ですか？いやー、予想以上に細いですね。
This is an image of Himiko, as seen by Hubble. It's just a raw image, with the noise not yet eliminated. But Ouchi can see at a glance that this stick-like object is far longer and thinner than he'd imagined. The size, again, measures the same with Hubble as with the Subaru telescope. At 50,000 light-years across, it is indeed gigantic. Himiko, the largest known distant celestial object, Hubble has taken us one step closer to unraveling its mysteries.
思った以上に細長い天体になってる。これは予想してなかったことですし、これはどうしてなのかなっていうのは今後ちょっと詳しく調べていきたいと思っています。
The next steps will be to eliminate the noise in the Hubble photograph and then to superimpose various color filters. When a fully refined picture of Himiko has emerged, it may solve one of the riddles of the frontiers of space. The Hubble Space Telescope, product and symbol of our questing spirit, our longing to fathom the mysteries of the universe. Hubble has already shown us that the universe is comprised of a seemingly endless patchwork of giant bubbles. But there remain mysteries that go beyond our wildest imaginings. Mysteries that are waiting for us to discover them. Humankind has only just begun to challenge the cosmic front.